Welcome, my friend. Tonight, let us drift together into the hidden fabric of reality. A realm where the smallest things in existence dance to rules unlike anything we know from the everyday world. Over the next 2 hours, we will wander softly through these mysteries, exploring how the tiniest threads of matter and light weave the grand tapestry of the universe. From strange dualities to whispers of entanglement, each idea will unfold slowly, so that you may both learn and, if you wish, gently fall asleep as the story of the quantum world carries you away. And as we wander, we will pause often, the way one lingers at a window on a night train, noticing how each new landscape becomes part of a larger, soothing journey. So, find a comfortable place. Allow your body to settle, your breath to slow. Imagine yourself afloat upon a quiet cosmic sea. Here, the strangeness of quantum physics becomes less a puzzle to solve, and more a lullaby of wonder to rest within. If a word or idea feels unfamiliar, let it pass like a soft tide over smooth stones. Clarity will arrive, patient and unhurried, as the shoreline of meaning gradually reveals itself. At its heart, quantum physics is the science that tries to describe the behavior of the smallest building blocks of nature, atoms, electrons, photons of light, and the elusive particles that dwell beneath them. Unlike the familiar laws that govern planets, falling apples, or the flow of rivers, the rules at these scales are unlike anything our intuition prepares us for. Here, certainty gives way to shimmering probabilities, and matter itself seems to ripple between possibilities. In simple terms, quantum physics tells us not exactly what is, but how likely it is that we will find something to be a certain way when we look. At the dawn of the 20th century, many believed physics was nearly complete. Newton's laws of motion had guided us for centuries. Maxwell's equations described the play of electricity and magnetism, and the principles of thermodynamics explained heat and energy with great clarity. To some, it seemed as though science had tied a neat bow around the cosmos. Only the finer details remained, or so they thought. It was as if a grand library had been catalogued from floor to ceiling. And then, quite suddenly, a hidden door opened to a new wing no one had noticed. But then, small cracks appeared in this confident edifice. Experiments began revealing puzzles that the old framework simply could not explain. One of the earliest mysteries came from the study of what was called black body radiation. Imagine, my friend, an ideal surface that absorbs all light and heat and then glows purely in response to its own temperature. According to classical thinking, such a body should release ever-increasing amounts of energy as its glow shifts to shorter wavelengths, leading to an absurd infinity of radiation in the ultraviolet range. This paradox became known as the ultraviolet catastrophe. In plain words, the math predicted a blinding, impossible glare that nature simply didn't produce. Yet nature refused to behave that way. Careful measurements showed that the glow rose, peaked at a certain frequency, and then fell away again. The old equations failed. Something new was needed. And so, for a moment, we pause to imagine the night sky, not a single unbroken brightness, but a curve of light with a gentle crest, a hint that reality prefers balance over infinity. In the year 1900, a German physicist named Max Planck offered a daring idea. Instead of imagining energy flowing in a smooth, continuous stream, he suggested that it came in little packets, like droplets of water falling one by one. He called these packets quanta. It was a radical thought. That energy itself was granular, not infinitely divisible. Planck introduced a tiny number, now called Planck's constant, to capture this new rule of nature. Though at first some thought it was merely a mathematical trick, this constant became one of the most fundamental anchors in all of physics. Said simply, the universe keeps time with a very small metronome, and that beat sets the size of nature's smallest steps. Planck himself was a reluctant revolutionary. He once said that he did not seek to invent a new theory, only to rescue the old one from contradiction. And yet, in trying to save classical physics, he laid the cornerstone of a new world. His constant, though tiny, unimaginably small, became the universal whisper that set the rhythm of atoms, photons, and even the birth of the cosmos. A few years later, Albert Einstein extended Planck's insight while studying a curious phenomenon called the photoelectric effect. When light shines on a metal surface, it can knock electrons free, but experiments showed something deeply puzzling. Dim blue light could eject electrons instantly, while even the brightest red light failed entirely. According to classical theory, brightness alone should matter, yet it did not. Einstein explained this by suggesting that light itself is made of discrete particles, later called photons, and that each photon carries a specific quantum of energy. Only if that energy is above a threshold can it release an electron. As a household image, no matter how many pebbles you toss, you can't ring a bell unless each pebble is heavy enough to make it vibrate. This proposal not only explained the experiments, it reshaped our understanding of light forever. And in recognition of this leap, Einstein was awarded the Nobel Prize in 1921. Imagine, my friend, light behaving as both a graceful wave and a sharp-edged particle. It was unsettling, but also wondrous. And it was just the beginning. The stage was set for a new physics, one that would exchange absolute trajectories for delicate probabilities and rigid clocks for a fabric that softly breathes. As the years unfolded, the mystery deepened. Was light truly a wave, or was it a particle? The experiment seemed to whisper both answers at once. When physicists sent light through two narrow slits, it spread out like ripples on a pond, creating a delicate interference pattern of bright and dark bands. Only waves could do this. And yet, when the same experiment was performed with faint light, so dim that photons arrived one by one, the pattern still emerged over time. Each single photon somehow behaved as though it had traveled through both slits at once, interfering with itself. In everyday language, each photon acted like a tiny note that could harmonize with itself, building a pattern one dot at a time. This experiment, the famous double-slit test, became one of the central demonstrations of quantum strangeness. It is as if the photon, when unobserved, chooses to behave like a broad wave, yet when we attempt to peek and see which slit it passes through, it abruptly acts like a localized particle. Nature refuses to give us both pictures at once. This was not merely strange, it was profoundly unsettling. And soon, the same paradox appeared for matter itself. Electrons, thought to be solid particles, showed the very same interference. In one moment, they seemed to be little marbles with mass and charge. In the next, they spread out like ghostly waves of probability. It was as though nature had refused to be pinned down to a single description. The world, we learned, is like silk that can feel both like fabric and like liquid, depending on how you touch it. Physicists repeated the experiment with atoms, and even with large molecules containing dozens of atoms. Always, the interference pattern appeared, a whisper that wave-like behavior is not limited to light or electrons, but is a universal trait of matter. Only when objects become large enough, tangled with countless interactions, do these ghostly wave patterns blur into the solid behavior of the everyday world. This became known as wave-particle duality. Matter and energy could no longer be divided into neat categories. A particle could also be a wave. A wave could also behave as a particle. The universe, at its deepest level, was whispering to us in a language of both, and not either or. And so, for a moment, we pause to imagine two voices braided into one song. Distinct, yet inseparable. A reminder that reality can hold more than one truth at a time. To navigate such paradox, scientists crafted careful experiments and new mathematical tools. They learned to dim light to single photons, to guide electrons as gently as one guides a firefly in the dark, and to watch without swatting away the very things they wished to see. In plain terms, to understand the small, we had to learn to be soft. To make sense of this riddle, a new framework was required. One that would not simply refine old equations, but rather replace the very foundations of physics. In the 1920s, pioneers such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger each contributed their vision. Bohr proposed that electrons in atoms occupy discrete orbits, leaping between them only by absorbing or releasing quanta of energy. His model was like a ladder. Electrons could rest on one rung or another, but never between. Heisenberg, with bold strokes of mathematics, described a new way of seeing. Not by following precise paths, but by focusing on what can be observed and measured. His approach, called matrix mechanics, looked alien at first, a forest of symbols that seemed detached from physical intuition. Yet it captured the essence of quantum behavior. In plain words, Heisenberg taught us to focus not on invisible paths, but on the outcomes we can truly measure. Schrödinger, on the other hand, imagined electrons not as little dots circling a nucleus, but as waves described by a flowing equation that came to bear his name. The Schrödinger equation was less rigid than orbits. It painted electrons as clouds of possibility, regions where they are more or less likely to be found. In plain speech, instead of tracing a bead on a wire, we learn to describe a cloud that changes and sings. Together, these ideas crystallized into what we now call quantum mechanics. The new approach did not banish the past so much as complete it, like adding a missing harmony to a familiar melody. The old notes still played for planets and pendulums, while the new notes carried the tune for atoms and light. It was a revolution unlike any other. Suddenly, the solid atom became a hazy cloud of probabilities. An electron no longer had a definite position and momentum at once, but instead a spread of possible outcomes, only collapsing into certainty when observed. The act of measurement itself became part of the story, not an external detail. Put simply, nature offers many maybes until a question is asked and then grants one answer, chosen according to quiet odds written in the wave. One experiment in particular brought these ideas vividly to life, the Stern-Gerlach experiment. In 1922, two physicists sent silver atoms through a magnetic field and discovered that the atoms did not spread smoothly, but split into two distinct spots. This revealed that certain quantum properties, in this case spin, could only take on discrete values. The world, at its smallest, does not slide along a continuum, but clicks into place like keys on a piano. And so, my friend, a new view of reality began to dawn, a universe woven of uncertainty, shimmering with potential, alive with paradox. A universe where the very act of looking could help decide what is real. Let this be a comfort. If the foundations of the world can be both soft and true, then so can our understanding, gently widening and deepening with each careful glance. As our picture sharpened, we discovered that particles were not the whole story. Beneath each dot was a field, a spread-out presence filling space like a fabric that can be plucked to produce notes. Next, we turn to this deeper layer, where reality resembles not a bag of marbles, but an ocean of ripples. Imagine, my friend, the night sky stretching endlessly above you. Stars glimmer like scattered lanterns, yet beneath that visible beauty lies something far deeper, an invisible sea of fields rippling through space. In the old picture of physics, the world was made of particles, tiny marbles darting through a void. But quantum theory urged us to look again. It suggested that what we call particles, electrons, photons, quarks, are not solitary beads at all. They are crests upon vast underlying fields, like waves rising from an unseen ocean. In simple words, a particle is a wave peak the universe allows us to catch. Each type of particle corresponds to its own field. There is an electron field, a photon field, a field for quarks, even for the elusive neutrinos. These fields span all of space and time, interwoven like threads in a cosmic tapestry. What we observe as a particle is really just a localized vibration, a knot of energy pulled from the continuous fabric. If the fabric is plucked in one place, a ripple runs outward. When that ripple is caught by our instruments, we call it a particle and give it a name. This picture reshaped the way scientists thought about matter. Instead of asking how a particle travels, one asks how a field fluctuates, how its ripples collide, interfere, and exchange energy. The universe becomes less like a collection of billiard balls and more like a grand symphony of vibrating strings. And so, for a moment we pause to imagine a wind moving through a wheat field. Nothing solid, jumping from stalk to stalk, only waves passing, carrying information from one place to another. To make this vision precise, physicists developed what is now called quantum field theory. At its heart lies the realization that energy is not smooth and unbroken, but comes in discrete steps, like rungs on a ladder. A field can vibrate only at certain levels, and each vibration manifests as a particle we can detect. In plain language, fields play notes, and each pure note, when heard, is a particle. The mathematics tracks how those notes combine, sometimes harmonizing, sometimes cancelling, much as overlapping ripples on a pond can build or soften the water's surface. Consider the photon, a quantum of the electromagnetic field. Light is not simply a continuous glow, but a stream of these quanta. They dance and collide, carrying energy from the heart of the sun to the eyes that now read these words. In the same way, electrons are quanta of the electron field, and so on for all the known particles. When fields nudge one another, their notes mingle, giving rise to chemistry, color, and the delicate scaffolding that lets matter hold its shape. And so, for a moment, we pause to imagine a silent orchestra becoming audible, each instrument waking in turn to play the world into being. There is one field whose quiet presence shapes us all: the Higgs field. Unlike other fields that usually rest at zero unless excited, the Higgs field keeps a gentle, persistent value everywhere, like a thin mist filling all space. Particles that coupled to it gain inertia, what we call mass, by drifting through this ever-present haze. The heavier the coupling, the more the field resists their motion. In ordinary words, the Higgs field is like a room filled with soft honey. Some dancers glide, others feel a tug. The discovery of the Higgs boson, a ripple in that field, confirmed the mist itself, a tender proof that the invisible backdrop is real. Let that thought settle like dew, unseen, and yet everything glitters because of it. And in this restless stage, my friend, reality takes on a new shimmer. The world around us is not built from solid pieces, but from the ceaseless trembling of fields that are everywhere, all the time. Even in perfect emptiness, the fields do not fall silent. They hum faintly, whispering the possibility of creation and annihilation at every instant. This hum is not noise, but a steady background, a faint, cosmic breathing beneath all things. If the vacuum hums, then its quietest fluctuations will sometimes leave fingerprints. We call these fingerprints virtual particles, not objects we can scoop up, but brief visitors that shape what we see. Let us step closer to those whispers now, with the gentleness one brings to fireflies at dusk. Close your eyes for a moment, my friend, and picture the silence of a midnight sea. At first glance, the water seems calm, its surface still. But if you look more closely, you notice tiny ripples, quick shimmers that come and go before you can focus on them. In the quantum world, even the so-called vacuum is never truly empty. It, too, flickers with such momentary disturbances, restless whispers of existence we call virtual particles. Think of them as brief footfalls in soft sand. The traveler is gone, but the imprint remains just long enough to matter. These fleeting entities are not particles in the usual sense. They cannot be plucked out and placed in a jar. They do not march across space in a measurable line. Instead, they arise as temporary fluctuations within fields, like foam bubbling on top of a deeper wave. They appear for the briefest moment, borrow energy from the field, and then vanish again, always within the strict bounds of quantum law. In plain words, nature allows tiny loans of energy if they are repaid quickly, and those loans leave subtle effects we can measure. Though invisible, their influence is immense. Virtual photons, for instance, mediate the electromagnetic force, passing momentum between charged particles like secret couriers. Without them, atoms would not hold together, light would not scatter, and electricity would not flow. Other virtual particles play similar roles in the strong and weak nuclear forces, binding protons in the heart of the atom, or guiding radioactive decay. When magnets pull or ions bond, you are feeling the handshake of fields conducted by these brief messengers. We learned to trust these whispers through their fingerprints. One is the tiny shift in hydrogen's energy levels, known as the Lamb shift. a small detour from classical expectation caused by vacuum fluctuations nudging the electron's orbit. Another is the Casimir effect. Two uncharged metal plates placed very close together feel a gentle push, as if the vacuum itself were pressing them. And around a charged particle, the vacuum polarizes. Virtual pairs briefly screen the charge, altering the force's reach by the smallest of degrees. Each effect is a delicate, testable bias in nature's otherwise balanced ledger. And so the modern view of the universe includes this hidden population of ephemeral actors. They remind us that even emptiness is alive with motion, that the very fabric of reality is a restless weave of appearance and disappearance. As you drift deeper into calm, let this idea settle like a gentle tide. Nothingness itself is never still, but always humming with the quiet promise of possibility. For a moment, we pause and imagine the space between heartbeats filled with a soft, sustaining murmur. There is, however, a challenge. When we add up the influence of countless fluctuations, the numbers can swell beyond reason. To make sense of this, physicists learned a careful craft: to separate what is measurable from the mirrored echoes that do not touch the instrument's face. Imagine gazing into a mirror that reflects another mirror behind you, my friend. The image stretches away in endless repetition, smaller and smaller, until it vanishes beyond sight. This feeling of infinity, beautiful yet overwhelming, echoes a deep challenge in quantum physics. When physicists first tried to calculate the effects of virtual particles, they were confronted with numbers that grew without bound, infinities that threatened to shatter the entire framework of the theory. In simple terms, the math said too much, while nature kept saying just enough. For a time, this was deeply troubling. A calculation that predicts infinite energy for an electron or limitless strength for a force cannot describe the real world. Nature, after all, is finite and balanced. Yet within the equations of quantum electrodynamics, infinities appeared everywhere, like an echo chamber that refused to stop amplifying. The problem was not in the music, but in the room where it was being played. The solution, though daring and subtle, came in the form of a method called renormalization. Rather than discard the theory, physicists realized that some of these infinite quantities could be absorbed into the very definitions of mass and charge. By carefully subtracting the divergences, what remained were predictions that matched experiments with astonishing precision. In everyday language, we learned to calibrate our rulers and scales, so that the measurements reflected what we can actually observe, not the endless reflections within the mirrors. Think of it as cleaning a tangled loom of threads. At first, knots appear everywhere, a hopeless mess. But by reworking the weave, pulling and shifting in just the right way, the tapestry reveals its true pattern. Renormalization was not a trick of avoidance, but a revelation that physical quantities we measure, the mass of an electron, the strength of its electric charge, already include the influence of countless hidden fluctuations. The bare quantities are never seen. The dressed, physical ones are what touch our instruments and our lives. This careful craft does more than remove infinities. It shows that some forces change their apparent strength with energy. We call this running. At very high energies, the electromagnetic force grows slightly stronger, while the strong force grows weaker, a preview of deeper unity. The most famous triumph here is the prediction of the electron's anomalous magnetic moment. a tiny deviation from simple theory, measured and calculated to astonishing agreement. Digit after digit aligning like stars in a crisp night sky. There is, however, a quiet philosophical lesson. Infinity did not disappear. It was tamed, reframed, given meaning by how we define what is measurable. In this way, renormalization reminds us that the universe is not only about what equations declare, but about how we choose to connect those equations with what we can touch, see, and know. And so we pause to appreciate the humility of measurement. Not everything that can be written can be weighed, and not everything that can be weighed should be taken as the last word. As you rest deeper into the stillness of this night, think of renormalization as a kind of cosmic balance, a way of turning overwhelming infinities into a harmony of finite truths, much like calming waves on an endless shore. The sea remains endless, yet the tide that reaches our feet is gentle, measured, and kind. Having learned to read the trembling fabric, we now journey inward, past atoms and into the cores of protons and neutrons. There, a stronger music plays, fierce, binding, and exquisitely ordered. Picture, if you will, my friend, the heart of matter itself. Not the atoms, nor even the protons and neutrons within them, but the restless interior where quarks and gluons perform their eternal dance. This hidden realm is governed by a theory called quantum chromodynamics, or QCD for short, a framework as rich and colorful as its name suggests. In plain terms, QCD is the rulebook for the strongest force we know, the one that stitches the nucleus together. Unlike electrons, which whirl around nuclei like ripples in a vast pond, quarks are bound within protons and neutrons, never seen alone. They cling together through the exchange of gluons, particles that carry what physicists poetically call color charge. This is not color as our eyes perceive, but a metaphor drawn from red, blue, and green. Three basic charges that must always blend into neutrality, much as the mixing of paints yields white. If the colors don't balance, the force pulls until they do. The force binding quarks is unlike any other. With electricity, the farther apart charges drift, the weaker the pull becomes. But in QCD, the reverse is true. Stretch quarks apart, and the tension grows like an elastic band pulled tighter and tighter. Eventually, the band snaps, not by releasing its captives, but by birthing new quark-antiquark pairs from the vacuum itself. This is why quarks can never be isolated. The very act of trying to separate them summons new companions, ensuring that confinement remains absolute. Said simply, pull on the fabric hard enough, and the cloth mends by weaving new thread. At small distances, however, something remarkable happens. The strong force weakens, allowing quarks to flit almost freely within the cramped interior of protons. This phenomenon is known as asymptotic freedom. The paradox that the closer quarks come, the less they seem to notice one another. It is a principle confirmed in the high-energy collisions of particle accelerators, where jets of particles emerge as fleeting evidence of quarks and gluons inside. The recognition of asymptotic freedom earned its discoverers the highest honors, a quiet bow from nature, acknowledging a truth long hidden in the nucleus. We probe these mysteries in many ways. In heavy ion colliders, gold or lead nuclei are smashed together at near light speeds, briefly melting protons and neutrons into a quark-gluon plasma, a droplet of the early universe, hot and fluid, where quarks roam before confinement reasserts itself. On powerful computers, lattice QCD places spacetime on the grid, allowing us to simulate how quarks and gluons stitch hadrons together. Each method is like a different lantern, together illuminating a dance we can never see directly. QCD is not merely a tale of confinement and freedom. It is also a story of the very stability of matter. Without the strong force gluing quarks together, protons and neutrons would unravel, and the atoms of our world would dissolve into a sea of fragments. It is this force, fierce and unyielding, that shapes the nuclei of stars, that fuels the fire of creation, and that ensures the universe has structure rather than chaos. Even the light that warms your skin is born in processes. The strong force makes possible deep within stellar cores. And yet, in the softness of this reflection, there is beauty in the paradox. A force so strong it will not let go, yet so subtle it allows the world to exist in delicate balance. The dance of quarks and gluons is hidden from view, but its rhythm sustains every breath, every heartbeat, every spark of starlight above. And so we pause to picture a tapestry's underside, messy knots and tight loops that, from the front, appear as calm, continuous art. When the strongest force finishes its song, the stage does not fall silent. The space between the instruments matters too. The vacuum itself, the in-between, contributes to the music we hear. Let us listen there now, with ears tuned to whispers. Settle deeper now, my friend, and imagine the quietest place you can. A cave beneath the mountains, a stretch of ocean at midnight, a chamber sealed from every sound. You might think of it as empty. Yet in the quantum world, emptiness is an illusion. What we call a vacuum is not stillness, but a restless ocean, a sea of fields, forever rippling with unseen fluctuations. In simpler terms, the background is never truly background, it is a participant. Within this sea, particles appear and vanish in a ceaseless dance. They are the virtual particles we spoke of earlier, but here, their presence takes on a deeper meaning. These whispers of existence shape everything around us, even though we can never hold them in our hands. They alter the behavior of atoms, shift the orbits of electrons ever so slightly, and generate faint but measurable forces between objects that should, by classical reasoning, feel nothing at all. Think of fine dust motes in a sunbeam nudged by a breeze you cannot see. One such effect is the Casimir force. Imagine two perfectly smooth metal plates placed a hair's breadth apart in a vacuum. No air, no light, no matter between them. Classical physics would say there is nothing at all in that space. But quantum physics reveals otherwise. Virtual particles fill the gap unevenly, creating a subtle pressure that pushes the plates together. This invisible nudge is not fantasy. It has been measured in laboratories with exquisite precision. The very vacuum, once thought empty, reveals itself as an active, creative participant in the universe. In plain words, emptiness has a gentle hand. Even the spectrum of atoms bears the sea's imprint. The Lamb shift, tiny though it is, shows that the vacuum can tug on an electron's energy levels, moving lines in a star's light by the smallest of amounts. Around heavy nuclei, vacuum polarization slightly alters the strength of electric forces, an effect that makes theory agree with experiment as neatly as a seam pressed flat. Each is a small reminder the silence is singing. These whispers also ripple outward to cosmic scales. In modern cosmology, the energy of the vacuum, called dark energy, may be driving the expansion of the universe itself. A force born from the silence of nothingness is pushing galaxies apart, stretching space-time like a balloon. What was once considered the absence of being is now understood as one of the most profound sources of motion in the cosmos. Though we do not yet fully grasp its nature, we feel its tug in the way distant galaxies drift away like lanterns on a widening river. Let this idea soothe you. The universe is never static. Even in the void, life stirs. Even in silence, there is music. The quantum sea hums beneath all things, a hidden lullaby of creation, reminding us that from apparent nothingness, worlds can emerge. And so, we rest for a breath, imagining that each inhale is a small rising wave, and each exhale a gentle falling back into calm. When even emptiness behaves, our questions naturally turn to knowledge itself. How much can we know at once? What does it mean to measure, to ask, to find? Now we step into the soft boundary between knowing and not knowing, with patience as our guide. Close your eyes now, my friend, and picture yourself holding a delicate coin between your fingers. In the familiar world, you could flip it, catch it, and declare with certainty whether it shows heads or tails. But in the quantum realm, that certainty dissolves. The coin does not rest on one face or the other until you look. Instead, it drifts in a haze of possibilities, both heads and tails at once, awaiting the act of observation to bring it into focus. This is less a trick of vision than a property of reality. Before the question is asked, the answer is still a cloud. This is the heart of Heisenberg's uncertainty principle, a discovery that forever changed how we understand knowledge itself. At its core, it tells us that some pairs of truths, like a particle's position and its momentum, cannot both be known with perfect precision. To sharpen one is to blur the other. This is not a failure of our instruments, not a gap in our cleverness, but a fundamental limit woven into the fabric of reality. In simple language, you can know where or you can know how fast, but not both to perfection at the same time. A gentle way to feel this limit is through sound. A sharp clap, short in time, contains many pitches. Its frequency content is uncertain. A pure tone, perfectly steady in pitch, must last a long time, then its time of arrival is uncertain. This is the same trade-off dressed in music rather than motion. In mathematics, we say that waves and their spectra are tied by a Fourier transform, a bridge that turns shapes in one space into spreads in another. The principle is not an obstacle. It is the rhythm of how waves carry information. The Stern-Gerlach experiment gave this rhythm a face. When soother atoms passed through a magnetic field, their spins split into two beams, up or down, nothing in between. But if one measures spin along a different direction, the certainty vanishes. Prepare up along one axis, then measure along a tilted one, and outcomes become probabilistic. Knowledge in one frame blurs knowledge in another. As if each question puts on a different pair of glasses, each pair sharpening one view while softening the next. For centuries, physics was built on the dream of determinism, the belief that if we knew enough, we could predict everything. The planets, the tides, the fate of every grain of dust, all set in motion like gears in a clock. But Heisenberg's principle softened that dream. It told us the future is not written with perfect ink, but painted in strokes of probability. The universe is not a rigid machine, but a tapestry threaded with uncertainty, allowing for freedom, variety, and surprise. The clock still ticks, but its hands glide with a gentle blur at the edges. And in this realization lies something deeply human. To live is to face the unknown. To breathe is to accept limits. Even at the smallest scale, the cosmos whispers that certainty is not the essence of reality, wonder is. As you let this truth settle into your thoughts, feel the gentle reassurance it carries. You do not need to know everything to belong within the grand design. And so, we pause to imagine a lantern on a misty path. Enough light to take the next step, and that is enough. If we cannot know everything at once, perhaps reality itself keeps many options open. Next, we turn to the idea that the world holds several melodies at the same time, letting them play until one is chosen, soft as breath on a window pane. Imagine, my friend, a quiet pond at twilight. You toss 2 stones into the still water, and the ripples from each stone spread, overlap, and blend together. At some points, the ripples reinforce one another, rising high. At others, they cancel, leaving a calm hollow in the surface. This mingling of waves offers us a way to glimpse one of the most mysterious truths of the quantum world: superposition. In plain words, a quantum object can be in several allowed states at once, like overlapping ripples awaiting a gentle decision. In our everyday lives, we expect things to be definite. A door is open or closed. A lamp is either shining or dark. But in the quantum realm, particles like electrons and photons are not bound by such strict categories. Until they are observed, they exist in many states at once, like ripples combining on a pond. A single particle can be here and there, spinning one way and the other, traveling both paths through a maze simultaneously. Its existence is not confined to a single thread, but woven from overlapping possibilities. Schrödinger sought to dramatize this strangeness with the cat in the box. The thought experiment illuminates how odd it feels to extend quantum rules into daily life. In reality, everyday objects are tied to countless environmental interactions, air molecules, thermal vibrations, errant photons that quickly destroy delicate superpositions. This process is called decoherence. It does not choose an outcome, it simply smears the fragile harmony into separate, non-interfering melodies, making a single classical note all we can hear. In simple terms, the world's background noise makes quantum chords sound like ordinary tones. Experiments have pushed superposition to surprising sizes. Not only electrons and atoms, but large organic molecules, dozens, even hundreds of atoms, have flown through interferometers and produced patterns of self-interference. Each success is like balancing a soap bubble in a breeze. For a moment, many possibilities shine on one iridescent surface. When we look too closely, the bubble pops, and a single droplet remains. This principle reaches far beyond metaphor. It is the foundation of quantum technologies. Quantum computers rely on bits that can be both 0 and 1 simultaneously, exploring countless possibilities in parallel before collapsing into a final answer. Quantum sensors use superposition to measure time, fields, and acceleration with exquisite precision. In chemistry, superposed electron states shape the bonds that form the molecules of life. Even the colors of the stars depend on these layered possibilities inside excited atoms. At first, this may feel unsettling. A world where things are not what they seem, where reality floats in a mist until we look. But perhaps, my friend, there is comfort here too. For superposition whispers that potential is always richer than appearance. Beneath the surface of every moment lies a web of possibilities, shimmering, waiting to unfold. And just as the quantum world does not collapse until touched by observation, so too in our lives, possibilities remain alive until we choose our path. We are, in a quiet sense, composers of which melody will sound next. Close your eyes now and drift with that thought, that uncertainty is not emptiness, but abundance, that within the unseen weave of reality, many stories wait, and one by one, they gently become real. And so, we pause, breathing in, breathing out, letting options soften into ease. Sometimes, when possibilities touch, they never fully part. Two systems can become one tale, no matter how far they travel. Now we follow those threads across the dark. Now, my friend, let us step even deeper into the wonder. Imagine two tiny sparks born together in the same fire, then carried far apart. One drifting to the mountains, the other across the sea. Though distance separates them, they remain mysteriously linked, as if tied by an invisible thread. This is the essence of quantum entanglement, one of the strangest and most beautiful features of the quantum world. In simple words, once quantum systems become one story, you cannot read one page without touching the meaning of the other. When two particles become entangled, their properties are no longer independent. Measure one, and you instantly know something about the other, no matter how far apart they are. If one spin is found to be up, the other must be down. If one photon is polarized one way, its partner takes the complementary orientation. They are not two separate objects, but part of a single, shared system stretched across space. The correlation is not a message traveling. It is a relationship already written. Albert Einstein challenged this with a thought experiment, suggesting perhaps hidden variables carried secret instructions. Later, John Bell turned the question into a test, showing that any hidden instructions obeying classical limits would leave a specific numerical signature. Physicists performed Bell tests with entangled photons and again, found that nature violates the classical limit. Entanglement is stronger than any prearranged script. In later loophole-free experiments, distances were increased and choices were made rapidly and randomly, closing the door to easy escape routes. The verdict stayed the same. The world is more woven than classical threads can explain. This discovery challenges our deepest intuitions about separateness. In the everyday world, we believe objects are distinct, that one thing here cannot instantly affect something there without a signal passing between them. Entanglement breaks that boundary. It suggests the universe is more like an indivisible whole, where parts remain bound together even when they drift to opposite ends of the cosmos. The whole is not merely the sum of the parts, it is also the pattern that links them. Beyond philosophy, entanglement has practical power. It is the beating heart of quantum communication and quantum computing. Secure messages can be shared using entangled pairs, where any eavesdropping leaves telltale scars. Quantum repeaters and satellites have beamed entanglement across cities and between ground and orbit, hinting at future networks that braid the planet in fragile, luminous threads. What once seemed like a curious paradox now fuels the next frontier of technology. And yet, the greatest gift of entanglement may not be in machines, but in meaning. It whispers that the universe is woven from relationships, that nothing exists in isolation. Even across immense gulfs of space, particles remain connected, mirroring the quiet truth that we too are bound to one another, by gravity, by history, by consciousness, by the threads of being itself. As a human image, a family story told across generations still binds hearts that have never met. So, as you rest, imagine yourself a particle in this cosmic web, entangled with distant stars, with every life that has ever been, with every breath that will ever be drawn. The universe is not a scattering of fragments, but a single unfolding whole. And you, my friend, are part of its indivisible song. Let that song be a gentle cradle as night deepens. If the world can hold many notes at once, and if threads can bind those notes across space, what happens when a single note must be chosen? We turn now to the quiet moment when possibility narrows and reality arrives. Picture a great symphony, my friend, where every instrument plays at once: violins, flutes, drums, horns, all weaving melodies that overlap and intertwine. Before the conductor lowers the baton, the music is a blur of possibility, all sounds coexisting in a single swell. But then, with a single gesture, one harmony is chosen, and the rest fade away. This is how physicists often describe the collapse of the wavefunction, the moment when shimmering quantum possibilities resolve into a single outcome. In simple terms, many maybes become one event. In the language of quantum mechanics, the wavefunction is the mathematical description of a system in superposition. It holds every possible state, an electron here and there, spinning this way and that, all encoded in a single equation. But when we measure, we never see all the possibilities at once. Instead, we find only one. The act of observation collapses the wavefunction, reducing many potentialities to a single reality. The odds are set by the wave. The outcome is a single draw. This raises haunting questions. Does the universe choose an outcome only when we look? Is the act of measurement a partnership between the observer and the observed, an intimate dance that brings reality into being? Or is collapse simply the appearance of choice, while the deeper truth continues branching unseen? In plainer language, is the world deciding, or are we simply discovering which page of a many-paged story we inhabit? Some interpretations, like the Copenhagen view, suggest that measurement itself calls reality into focus, that until we look, the world is unresolved. Others, like the many worlds interpretation, propose that every possibility unfolds, each in its own branching universe. Countless parallel realities, forever splitting, each one as real as ours. Still others appeal to interactions with the environment, decoherence, to explain why the many harmonies quickly sound like a single note to us. There are even reflections like Wheeler's delayed choice ideas, where our present questions seem to reach backward, deciding whether light behaved like a wave or a particle long after it passed. Not changing the past, but choosing which story about it becomes relevant. Whatever the answer, the collapse of the wave function reminds us that certainty is not a given, but an event. Reality does not lie waiting, fully written, it crystallizes in the moment of encounter. A photon is not here or there until its path is traced. A particle's spin is not up or down until the result is known. The universe does not present us with a fixed script, but a flowing improvisation, alive with choice and surprise. Think of opening a book where the ink dries as you read. The story forms beneath your gaze. And so, as you drift into deeper rest, let this idea wash over you. The future is not already sealed. It waits, shimmering with possibilities, until the moment you meet it. Each choice, each observation, collapses a wave into the world you walk through. Life, like quantum reality, is not a closed book, but a story forever being written. And that, quietly, is hope. Choices arrive, and sometimes they find us facing barriers. In the quantum world, even barriers are not always final. There are secret doors in the stone. Let us walk to one now. Imagine, my friend, standing before a mountain wall, tall and unyielding. In the world of our everyday senses, you and I know what happens next. Unless we climb or carve, we cannot pass. The rock is solid, the barrier absolute. Yet in the quantum world, particles are not bound to such finalities. They slip ghost-like through barriers that should have held them fast. This is quantum tunneling, one of the most astonishing gifts of the microscopic realm. In plain words, a particle's wave can leak through a door that seems shut. At its heart lies the wavefunction, not a fixed path, but a cloud of probabilities. When a quantum particle meets a barrier, its wave does not stop abruptly. Instead, like ripples pressing against a shoreline, it seeps partway into the forbidden region, fading but not vanishing. And if the barrier is thin enough, or the energy just close enough, part of that wave continues on the far side. Against classical expectation, the particle has tunneled through, appearing where it had no right to be. This is not a cheat, it is the world honoring the rules it set for waves. This is no phantom trick. In scanning tunneling microscopes, sharp metal tips hover close to a surface, and electrons tunnel across the tiny gap, producing currents so sensitive that we can map individual atoms. In stars, tunneling allows hydrogen nuclei, ordinarily repelled by their electric charge, to slip close enough to fuse, igniting the furnaces that make suns shine. Without tunneling, our own star would never burn with such warmth, and we would not be here to ponder its light. There are quieter marvels too. In superconductors, pairs of electrons tunnel together across thin barriers, creating a current with no resistance. The Josephson effect, a kind of quantum whisper that circles forever without fading. In nuclear physics, alpha particles tunnel out of heavy nuclei, setting their half-lives like softly ticking clocks. And in chemistry, light particles such as protons sometimes tunnel within enzymes, speeding reactions that sustain life. Each is a door opening not by force, but by possibility. And perhaps, in a gentler metaphor, tunneling whispers to us about our own lives. Barriers that seem immovable may, at times, be crossed not by brute strength, but by persistence, chance, and the subtle weaving of possibility. Just as particles find themselves on the other side of an impossible wall, so too might we awaken one day beyond a difficulty we once thought insurmountable. Sometimes the way through is not over or around, but softly, mysteriously through. So, as you breathe softly and sink deeper into rest, remember, even in the most solid-seeming world, there are hidden passages. The universe itself shows us that nothing is final, that even the hardest walls can, under the right conditions, be gently passed through. Let that be a kind thought to carry into sleep. When passages open by probabilities' grace, we learn to count chances rather than certainties. The next chapter is the grammar of that counting. Clear, reliable, and quietly beautiful. Let us pause for a moment, my friend, and listen to the quiet rhythm beneath all quantum things. Unlike the firm steps of classical physics, where one can predict exactly where a planet will be or how a pendulum will swing, the quantum world speaks in a softer tongue, the language of probability. In everyday terms, nature gives odds, and then plays fair with them. In this realm, certainty is rare. Instead, each particle is described by a wavefunction, a mathematical cloud that spreads across many possibilities. The brightness of the cloud at any point tells us the likelihood of finding the particle there, not its definite location. Roll the dice once, and you cannot say what will come. Roll them many times, and the pattern of chances emerges. So too with electrons, photons, and quarks, each event is uncertain, yet the overall patterns are as precise as the ticking of a clock. The single toss is surprise. The many tosses are law. The rule that turns wave brightness into detection odds is called the Born rule. It says, simply, that probabilities are given by the square of the wave's amplitude, a compact way of telling us how often each possibility will be realized if we repeat the setup again and again. No one asked the universe to choose this rule. We discovered it, as one discovers the meter of a poem already written. This probabilistic nature is not a flaw in our understanding. It is the way the universe truly behaves. Even if we had perfect instruments, even if our minds were limitless, we could not pierce beyond it. The uncertainty principle, superposition, entanglement. All these features point to a cosmos that is woven not from absolutes, but from weighted possibilities. Probability is not a concession, it is the blueprint. And remarkably, this language of chance is astonishingly powerful. Quantum mechanics can predict, with extraordinary accuracy, the spectral lines of atoms, the behavior of semiconductors, the lifetimes of unstable particles. The randomness of each outcome balances with the reliability of the whole, much like individual raindrops forming the predictable arc of a rainbow. A single raindrop is chaos. A shower is a pattern your skin can learn. For us, there is a gentle lesson hidden here. Life, too, is written in probabilities. We cannot foresee every moment, cannot control each twist of fate. But across the long arc, patterns emerge, growth, renewal, the quiet return of dawn after every night. Just as the quantum world embraces chance yet still creates order, so too does our own journey unfold with both unpredictability and grace. We can plant seeds, not guarantees, and yet gardens still bloom. So rest in the comfort of this truth. Uncertainty is not chaos. It is a deeper kind of order, one that allows freedom and variety while still holding to balance. The universe, in its quiet wisdom, has chosen probability as the brushstroke with which to paint reality. And so we exhale, trusting that the picture fills in even when we cannot see every stroke. If probability is the grammar of the small, then technology is its poetry made practical. Now we turn to the instruments in our hands, the places where quantum rules become daily life. The story of quantum physics is not only one of abstract wonder, my friend, but also of very real tools that shape our daily lives. From the tiny transistor in your phone to the vast networks that guide satellites across the sky, quantum rules whisper beneath every circuit and signal. The modern world hums in quiet duet with the atom. Consider the transistor, the building block of modern electronics. Its delicate layers of material guide the motion of electrons, and the behavior of those electrons cannot be described by classical laws alone. Instead, it is quantum mechanics, the quantized energy levels within semiconductors, that makes it possible for these devices to switch on and off, forming the digital language of zeros and ones that powers our age. A transistor is a small gatekeeper that speaks in quantum syllables to say yes or no millions of times each second. Lasers, too, are children of quantum ideas. By coaxing atoms into precise states of excitation, we harness their release of photons in perfect synchrony. The result is a beam of light, coherent, sharp, and focused, a quantum chorus singing in unison. That same principle guides data pulsing through optical fibers, the readout of barcodes, eye surgeries drawn with light, and the steady hands of industrial cutters. Coherence, all waves in step, is the secret that turns glow into precision. Look also to medicine. Magnetic resonance imaging, or MRI, allows us to see inside the human body without a single incision. It depends on the tiny magnetic spins of atomic nuclei, aligning and relaxing in fields, whispering back signals that reveal the hidden landscape of organs and tissues. This is quantum mechanics at work, not in distant laboratories, but in hospitals, bringing relief and understanding. In simple terms, your atoms sing when placed in a magnetic choir, and we turn their song into pictures that heal. Atomic clocks, ticking to the rhythm of electron or hyperfine transitions, measure time so precisely that they lose less than a second across millions of years. They allow our satellites to synchronize, our navigation to remain true, and our shared sense of time to rest on something steady. Without them, maps would falter and global systems would stagger. With them, the planet keeps time from a quantum metronome. Peering toward tomorrow, we find quantum computation and communication. Superconducting circuits and trapped ions host fragile qubits held in superposition and linked by entanglement. Quantum key distribution sends single photons carrying secret keys. Any attempt to eavesdrop disturbs them, revealing the intrusion. Entangled links have reached between mountaintops and through satellites, hinting at a future quantum internet where information is shared in threads no thief can touch without leaving fingerprints. In all of these, the lesson is clear. What began as mystery has become mastery. The uncertainty and strangeness of the quantum world have not remained hidden in equations. They have been woven into the tools of everyday life, proving that even the most bewildering truths can be guided into harmony with human need. We do not tame the quantum, so much as invite it to sing in tune with our designs. As you drift into rest, remember the strangeness that once seemed unsettling now shines as opportunity. Quantum physics shows us that even the most alien rules can become allies, if only we learn to listen closely to the quiet song they sing. And we are learning, note by gentle note. Technology is not the only place where quantum rules matter. There are hints, tentative, fascinating, that living things may borrow these rules too. Let us visit that possibility with care and wonder. We often think of quantum physics as the province of distant laboratories or the cold interiors of particle accelerators. Yet its influence may reach into something much closer, much more intimate, the mystery of life itself. In recent years, scientists have begun to glimpse quantum effects woven into the fabric of biology, suggesting that even within living cells, the strange rules of the microscopic world may play a hidden role. In plain words, life may sometimes think in the algebra of the small. One striking example lies in photosynthesis. When sunlight strikes the leaves of a plant, photons are absorbed and their energy must travel swiftly through a forest of molecules to the reaction center, where it can be stored as fuel. Classical physics would predict a clumsy, wandering journey, much energy lost along the way. Yet experiments reveal an elegant efficiency, as though the energy chooses the best path instantly. Researchers believe that quantum coherence, a delicate form of superposition, allows the energy to explore many routes at once, settling on the fastest with near-perfect success. Think of a traveler who senses every road simultaneously and steps onto the one that leads directly home. Another possibility emerges in the realm of navigation. Certain migratory birds seem able to sense the Earth's magnetic field, guiding their journeys across continents. How could such a faint influence be felt so clearly? One theory suggests that entangled particles within proteins in the bird's eyes respond to magnetic fields, providing an inner compass guided by quantum effects. The sky, then, is not only light and wind, but also a map written in the ink of the very small. Even within us, whispers of quantum biology may stir. In enzymes, quantum tunneling may allow protons or electrons to slip through barriers, speeding reactions that sustain life. In the human brain, some researchers explore whether quantum processes could influence cognition, though this idea remains debated and unproven. The careful stance is best. Celebrate the promising hints, and let time and data decide which whispers are genuine songs. While the field is still young and full of uncertainty, it hints at a profound thought. Life is not separate from the quantum world, but a child of it. The same rules that guide photons and electrons also help flowers turn toward the sun. Birds find their way, perhaps even minds dream. The boundary between physics and biology softens like mist at dawn. For us, this offers a gentle reassurance. The strangeness of quantum mechanics is not confined to stars or microscopes. It is within every breath of oxygen, every heartbeat powered by energy first gathered from sunlight. We are not merely observers of quantum mystery, we are woven from it. The leaf and the light share a language, and we are fluent without knowing. So, as you rest tonight, let this idea cradle you, that life itself may be guided by the shimmer of quantum threads, connecting the deepest laws of physics to the tender miracle of a leaf unfurling, a bird taking flight, or a thought drifting into being. Quietly, we belong to both root and ray. When quantum rules help leaves drink light and birds cross oceans, it is natural to look up and ask, how far does the small reach? The answer is simple and astonishing. As far as the universe. Let us lift our gaze now, my friend, from the small to the vast. For quantum physics is not only the story of particles and atoms, it is also the quiet architect of the universe itself. From the first instant of creation to the stars that burn above us tonight, quantum rules guide the unfolding of the cosmos. The tiny is the seed. The immense is the tree. At the dawn of time, in the earliest fraction of a second after the Big Bang, the universe was not a calm expanse, but a seething quantum froth. Fields fluctuated wildly, particles emerged and vanished, and uncertainty itself shaped the infant cosmos. Out of these fluctuations arose the seeds of structure, tiny ripples in density that, over billions of years, grew into galaxies, stars, and worlds. Without quantum randomness, the universe might have remained smooth and featureless, a silent ocean without islands of light. The freckles in the early fire became the constellations we trace tonight. In the hearts of stars, quantum physics continues its work. The process of fusion, where hydrogen nuclei join to form helium, is made possible by quantum tunneling, allowing particles to slip through barriers they could never overcome by brute force. Without this subtle trick, no star would shine, no element heavier than hydrogen would exist, and life would never have taken root. The iron in your blood and the calcium in your bones are poems written by quantum rules in stellar script. At the edge of gravity's extremes, quantum ideas light the dark. Black holes, those deep wells of space-time, should be perfect traps. Yet by subtle quantum processes near their horizons, they are predicted to leak a faint glow, a whisper of radiation that slowly carries energy away. Even where gravity rules, the small still speaks, reminding us that no realm is beyond the reach of quantum law. Even the very fabric of space-time may carry quantum echoes. Physicists dream of a quantum theory of gravity, one that unites the large-scale curvature of Einstein's relativity with the small-scale probabilities of quantum mechanics. Though still out of reach, this quest is born from the conviction that the universe is not built in layers of contradiction, but as a seamless whole. One day, perhaps, the ripples of space-time and the ripples of fields will be sung in a single score. And so we find ourselves suspended between scales. On one side, the quantum realm of electrons, quarks, and photons, fleeting, uncertain, shimmering with possibilities. On the other, the cosmic realm of galaxies, black holes, and expanding space. The miracle is that both are threads of the same tapestry. The smallest fluctuations shaped the largest structures. The tiniest probabilities became the story of everything. Like a loom that turns fine threads into vast cloth, the universe shows how tenderness builds grandeur. For us, there is a humbling comfort here. To look inward into atoms is to glimpse the same laws that govern the stars. To look outward into galaxies is to see the grand consequence of quantum seeds. We are neither separate from the small nor the large, but beings of both, children of the quantum and the cosmic alike. We are, quietly, the meeting place of dusk and dawn. So, as you rest beneath the silent sky, remember, every star you see was born from quantum chance. Every breath you take carries the imprint of processes written in quantum script. You are not apart from this vast universe. You are one of its most intricate expressions. And in the hush, this belonging is a comfort like a blanket laid over tired shoulders. We have walked far, from Planck's gentle steps to the glow of stars. What remains is not an ending, but a shoreline where questions lap like waves. There is grace in standing there, listening. And so, my friend, our journey brings us here, to the edge of what is known, and to the vastness of what still lies beyond. We have wandered through the quantum world, from photons and electrons to entanglement and tunneling, from the hidden whispers of the vacuum to the blazing furnaces of stars. And yet, for all we have learned, the heart of quantum mechanics remains wrapped in mystery. Mystery is not a flaw, it is the spaciousness where new understanding can breathe. Why does observation collapse the wave function? Are there hidden worlds branching with every possibility, or is reality truly shaped only in the moment we look? How does quantum uncertainty weave into gravity, time, and the fabric of space itself? These questions have no final answers. Not yet, perhaps not ever. And in that uncertainty lies both frustration and wonder. The unknown is a night sky, dark, yes, but studded with invitation. The people who carried these questions were human, with doubts and dreams. Max Planck, cautious and diligent, proposed quanta almost as a last resort to fit stubborn data, a reluctant revolutionary. Albert Einstein, who made light into particles, later resisted the idea that chance was fundamental, sparring gently with Niels Bohr at the Solvay conferences, like two master chess players smiling over the board. Bohr spoke of complementarity, the thought that wave and particle pictures, though mutually exclusive, are both necessary to tell the whole truth. Their debates did not end the mystery. They refined its edges, turning confusion into fruitful wonder. For the quantum world teaches us something deeper than equations. It reminds us of humility. That nature is not obliged to fit the comfort of our intuitions. That even the most brilliant minds must sometimes sit in awe before mysteries that refuse to resolve. And that unknowing is not a failure, but a space where imagination, curiosity, and discovery can grow. In simple words, we are students of a patient teacher. In a way, this mirrors our own lives. We too are built of uncertainty. We cannot predict every turn of the road, nor collapse the wave function of our own futures until we walk into them. And yet, like particles shimmering in superposition, we carry within us possibilities far richer than what appears at first glance. We choose, we learn, and the next path appears, not all at once, but exactly when needed. So, let us not fear the unknown, but rest within it. Let us cherish the beauty of questions that may never be answered, and the wonder of a universe that will always exceed our grasp. For it is in that exceeding, in that overflow of mystery, that life becomes vast and meaningful. The unanswered is not a void, it is a horizon. As you drift now towards sleep, hold this thought gently. The universe is not a closed book, but a story still being written. Its quantum pages shimmer with probabilities, waiting for the touch of observation, for the turning of time. And you, my friend, are part of that unfolding story. A fleeting yet eternal note in the great mysterious symphony of being. Rest well, and let the quiet hum of the cosmos carry you into dreams filled with starlight. Before drifting deeper, we pause to honor the quiet craft of experiment. The patient hands and careful lenses that turned ideas into evidence. What follows are gentle portraits of three touchstones, the double slit, the Stern-Gerlach, and Bell's tests. Each is a lantern hung along a forest path, making the way visible step by deliberate step. Imagine a wall with two narrow openings and, beyond it, a softly glowing screen. We send light toward the slits and watch the screen. With both slits open, we do not see two bright bands, as pebbles thrown through two doorways might suggest. Instead, we see many alternating bands. Bright, dark, bright again. The signature of interference, as if waves from each slit have overlapped, sometimes crest to crest, sometimes crest to trough, building and cancelling. This is the wave's handwriting. Now we dim the light until only one photon travels at a time. Common sense whispers that with single particles, the woven bands should vanish. Yet the screen slowly fills with dots that, hour by hour, assemble the same interference pattern as before. Each photon writes one dot, and together they sketch a wave's design. In plain words, the universe lets single notes compose a chord. Curiosity asks a natural question: which slit did each photon use? When detectors are placed to learn the path, the interference fades. The pattern on the screen becomes two simple lumps, as if the photons now choose a slit and travel like tiny pellets. The act of acquiring which way information changes what can be seen. The harmony collapses to a melody. We can have the pattern that reveals wave-like behavior, or the knowledge that reveals particle-like behavior, but not both at once. And so, for a moment, we pause to imagine a theater where the play changes the instant the audience asks who the actors really are. Later refinements made the story even gentler and stranger. In delayed choice versions, the decision to keep or erase path information is made after the photon has passed the slits. Yet still, the final pattern respects the choice. The past is not rewritten. Rather, the story we can consistently tell about the past depends on the present question. The world does not contradict itself. It waits to see which question will be asked and then answers in a way that remains softly self-consistent. Spin is a quantum property that behaves a bit like a tiny compass needle, an intrinsic twist that gives particles a magnetic personality. To reveal it, we picture silver atoms flying through an inhomogeneous magnetic field, one that is stronger at the top than at the bottom. If the atoms carried ordinary little bar magnets pointing in every possible orientation, the beam would smear into a vertical smear on the screen. But that is not what happens. Instead, the beam splits into two distinct spots, up and down, as if the atoms must choose between just two allowed orientations. This was the surprise of the Stern-Gerlach experiment. Spin is quantized. When the apparatus is rotated, and the test is repeated, the beam again splits in two relative to the new direction. Prepare up along one axis, then measure along a tilted one, and the results become a pattern of probabilities. The world's little compasses do not spin freely on a dial. They click into notches set by quantum rule. A sequence deepens the lesson. Select the up beam, send it through a second Stern-Gerlach device aligned the same way. Still up, a single spot. Now insert a third device in between, oriented sideways. It splits the beam into left and right. Take the left and pass it again through a final device aligned with the original direction. Surprisingly, it becomes both up and down with equal chance. Knowledge gained about one direction seems to unwind knowledge we had about another. In gentle language, each question lays down its own track, and new tracks can soften the prints of older steps. Entanglement suggested a connectedness stronger than any picture with hidden, pre-written instructions. But suggestion is not proof. John Bell found a way to test the depth of this connection by turning philosophy into numbers. He showed that any classical model with hidden variables must obey certain limits, inequalities that cap how tightly two distant measurements can correlate. Experiments with entangled photons set out to measure those correlations. First by Alan Aspect and collaborators, and later by teams that steadily closed every loophole, using fast, random choices of measurement settings, separating detectors by great distances and catching nearly every photon. Nature's answer was clear. The measured correlations exceeded the classical cap. Not by a noisy sliver, but by a steady margin that matched quantum theory. No signal raced faster than light. Rather, the results displayed a relationship that cannot be decomposed into separate local pieces. The pattern is less like two clocks synchronized at the start, and more like two notes that belong to the same chord even when played apart. And so, for a moment we pause to picture two distant bells struck in different towns, yet somehow chiming with a harmony that no local timing could arrange. The world remains causal and consistent, yet its fabric allows a togetherness deeper than intuition would grant. Experiments have voices, and theories have authors. The quantum story is also a human story, carried by people who puzzled, argued, yielded, and persisted. Let us meet them softly, not as statues, but as fellow night walkers. Max Planck moved carefully, a scholar who trusted data more than bravado. When he introduced quanta, he did not trumpet a revolution. He offered a measured bridge between stubborn numbers and a world that had not yet learned to be granular. He later wrote of an act of desperation, and yet, from that humility, modern physics took its first quiet step into the small. Albert Einstein saw in Planck's steps an opening for light itself. He gave the photon its clear voice, then went on to curve space and time. In later years, he resisted the idea that chance sits at nature's root, writing to a friend that God does not play dice. His skepticism sharpened the field, not by ending it, but by demanding clarity, a gift any science needs. Skepticism, handled with care, is a lantern, not a storm. Niels Bohr welcomed paradox with a calm smile. His idea of complementarity, that wave and particle pictures are both needed, though they cannot be applied at once, is less a solution than a posture of listening. With Bohr, physics became not just calculation, but philosophy, how we ask, what we can say, and where our language must soften to leave room for the world's own terms. Erwin Schrödinger wrote the equation whose flowing solutions still guide us today. He pictured matter as a wave, then challenged that picture with a cat who was neither plainly alive nor plainly dead until observed. His paradox has become a cultural touchstone, not to mock physics, but to remind us that our intuitions were grown in a different garden than the one atoms tend. Werner Heisenberg placed observables at the center, building a matrix mechanics that did not ask where an electron is, but what we can measure. From that stance came the uncertainty principle, not as a shrug of ignorance, but as a precise boundary line drawn by nature's own hand. Later, John Bell translated entanglement's mystery into a testable inequality, and Anton Zeilinger and many others lifted that inequality into the sky, sending entangled photons across mountaintops and between satellites and ground. Their work turned philosophical unease into crisp evidence, making the strange not only thinkable, but usable. And so, for a moment we paused to feel the warmth of their human presence. Letters exchanged, chalk dust on sleeves, late walks under cold stars. Their questions echo in ours, and their patience teaches us how to sit with wonder. From people, we turn to properties. The quiet rules that give particles their character, set the way they gather, and decide who may share a seat at nature's table. Spin, we have seen, is quantized, a built-in angular momentum, even when a particle is not whirling in any ordinary sense. Electrons carry spin 1/2, meaning that a full return to the same quantum state requires a 720-degree turn, a twice-around twist that defies cartoon expectation. Photons carry spin 1, their polarization dancing in full rotations. In plain language, different particles keep time to different turning rhythms. From spin flows a quiet but sovereign rule, the Pauli exclusion principle. Particles like electrons, protons, and neutrons, all with half-integer spin, called fermions, refuse to share the same quantum state. Two identical fermions cannot sit in the exact same chair. By contrast, photons and other integer spin particles, called bosons, welcome company. They happily crowd into the same state, brightening lasers and fostering superfluid flows. This divide, fermion and boson, is the architecture of matter versus light, solidity versus shimmer. Consider a simple atom. Electrons fill the lowest energy states first, 2 by 2, with opposite spins, then move outward to higher shells when the inner chairs are taken. That orderly filling gives us the periodic table, not a catalogue pulled from hand-waving, but a consequence of symmetry and spin. Wood, water, breath, bone, their textures and strengths, their capacity to hold shape, all root back to this gentle insistence that not every seat may be doubled. The firmness of everyday things is, in a deep sense, the quiet politeness of electrons giving one another space. And so we pause, picturing a theater where half the audience are solitary sitters and the other half crowd the aisles in a joyous chorus. From their different manners, the play itself takes form. Microscopic rules are tender, easily disturbed. Yet the world around us looks stable, classical, plain. What folds the many maybes into the single table before you? Let us listen to that soft soughing. Superposition is a chorus, but most of the time we hear only one voice. Decoherence explains why. A system, delicately prepared in a blend of possibilities, interacts with its environment, with air, with light, with warmth. Those interactions carry away the phase information, the threads that let one possibility interfere with another. The quantum harmony disperses into the world, not destroyed, but diluted into a pattern too fine for us to reweave. In simple terms, the room overhears the secret, and once the secret is everywhere, the duet cannot be separated from the murmur of the crowd. Decoherence does not pick a specific outcome. It merely prevents the different options from talking to one another. The effect is quick in warm, busy places, slower in cold, quiet laboratories, and slower still in the near-perfect hush of space. This is why cooling helps build quantum computers. Cold is not magic, but it is mercifully quiet. There is another gentle oddity, the quantum Zeno effect. If we ask the same sharp question again and again in very short intervals, "Are you still here? Are you still here?" we can slow the natural evolution of a system, even freeze a transition that would otherwise occur, like watching a pot that then paradoxically hesitates to boil. Frequent measurement arrests change. The world, it seems, becomes shy under constant, insistent attention. And so we pause to smile at a truth, both whimsical and exact. Sometimes, to let things happen, we must look away. We have spoken of change and pause, of freezing and flowing. Beneath these is time itself, the soft river that carries every note. What does quantum mechanics say about the river's bed? In quantum theory, time often appears as a parameter, a backdrop against which states evolve. The Schrödinger equation plays the role of a metronome, telling the wave function how to sway as time moves forward. Yet, in relativity, time is woven with space, curved by gravity, stretched by motion. Bringing these two views into a single, seamless fabric remains one of physics' most tender challenges. On a small scale, clocks can be made from quantum ticks. An atom's transition serves as a pendulum so steady that global time can be defined by its light. On the large scale, gravity makes those ticks run at different rates. Raise an atomic clock by a small height, and it will, measurably, run just a tiny bit faster. This is not poetry, it is experiment. Time, then, is not a single drum for all dancers. It is a field of many drums, each beating with a tempo set by place and motion, all kept in mutual tune by careful exchange of light. And so we pause to imagine a hillside of metronomes, each tapping at its own rate, yet all harnessed into harmony by patience and gentle coupling. The world's music is rich because its timing is varied and yet aligned. At the heart of many quantum tales is a subtler theme, information. What can be copied? What can be known? What can be carried without leaving a trace? Let us sit with these questions like stones warmed in the palm. A classical bit is crisp, 0 or 1. A quantum bit or qubit is a superposed blend of both until observed. A point on a sphere of possibilities rather than a pinprick at the poles. Entangle two qubits, and their fates intertwine so that learning about one reveals a matching pattern in the other. The power of quantum computation is not brute force. It is the artful shaping of these correlations so that the wrong answers cancel and the right one stands bright. A gentle but profound rule lives here, the no cloning theorem. Unknown quantum states cannot be copied perfectly. The proof is short and kind. Any attempt to duplicate every possible superposition would scramble the delicate phases that give the state its identity. In everyday language, you can take a photograph of a page, but you cannot Xerox a songbird's exact internal state while it is singing. The theorem protects security and sets limits on what can be stored or backed up in the quantum world. Yet there is a way to move a state without copying it: quantum teleportation. Using a shared entangled pair and two classical bits of information, the exact state of one qubit can be reconstructed at a distant location, while the original is necessarily destroyed in the process. No matter travels faster than light, rather, entanglement provides the mode, and the classical messages pour the plaster. The result is a perfect transfer without duplication. A rose pressed from one garden into another by a recipe that only works once. And so, for a moment, we pause to imagine passing a melody across a valley, not the air itself, but the instructions for reanimating the tune, guided by a harmony the two sides already share. Abstract rules become friendlier when we can touch their cousins in daily life. Waves, phases, interferences, we meet them every day without naming them. Let us visit those gentle cousins now. Stand at a window and tilt your head. Polarized sunglasses darken and brighten as the lenses rotate. Photons have polarizations, directions in which their electric fields shake. When two filters are crossed, only a little bit of light comes through. When aligned, much more light passes. This small, familiar dance is the macroscopic echo of quantum rules that, at the single photon level, produce the same patterns, one count at a time. Listen to two notes on the piano slightly out of tune, and you will hear beats. Waxing and waning volume as the waves drift in and out of step. Light does the same. Soap bubbles shimmer with color because films of slightly different thicknesses send reflected waves that interfere, cancelling some colors and enhancing others. A thin layer of oil on a puddle turns the street into a spectrum. A quiet, double slit played in miniature. The world is full of interference you can see and touch, soft reminders that quantum strangeness begins as ordinary wave sense, then grows delicate as we look smaller. Even the hush of noise-cancelling headphones uses interference, microphones listen, electronics craft an opposite wave, and the two sum to near silence. If you can feel quiet made by two sounds, you are already holding, gently, the idea that amplitudes add while probabilities emerge later. In simple words, what waves do first, chances reveal after. We have journeyed by equations left unspoken, hinted at by images and stories. It is worth saying once, softly, mathematics in physics is a map, rich and careful, that guides us through lands we cannot otherwise see. If you step outside now, in memory, in imagination, and look up, the sky is a page where quantum ink dried into constellations. In every photon crossing the night to your eye is a history, perhaps born in the heart of a star, by tunneling, perhaps scattered by dust in a faint interference that softened its path, perhaps redshifted by the gentle stretch of space. By the time it meets your retina, its wave function has flowed for ages, and then, with a whisper of collapse, it becomes one counted speck that tells your brain, there, a point of light. The table near you, steady and sure, is a parliament of electrons obeying exclusion, a calm upheld by restless fields. The warmth on your skin is a population of photons, born from the glow of matter, each carrying a little packet of energy. Planck once proposed with care. Your breath, in, out, is an oscillator, a simple harmonic motion whose quantum cousin is the most basic note in the theory's score. And so, for a moment, we pause to imagine the whole. Fields humming, probabilities guiding, decoherence sowing, information flowing, people wondering, instruments listening, and you, a listener among listeners, resting in the gentle center of it all. There would be new questions, there will be new lanterns. Perhaps a theory that marries gravity and quanta will arrive like a dawn after a long polar night, quiet and obvious once it is here. Perhaps the universe will keep a corner of itself forever tucked away, an invitation to humility. Either way, the song continues, and we are fortunate to have heard as much as we have. Now let your breath lengthen. Let your thoughts thin, like mist over a slow river. If a phrase returns superposition, spin, entanglement, let it be a feather settling, not a stone. The cosmos hums, your heart keeps time, the night is kind, the night is kind. Rest well, my friend, when dreams arrive. May they be stitched with gentle waves and threaded with friendly stars. My friend, we have reached the far horizon of our gentle journey. What began as a single doorway, Planck's small step into quanta, has unfolded into an entire landscape of waves, particles, fields, and mysteries. We have walked with photons and electrons, watched ripples interfere, followed atoms through magnetic fields, and seen distant particles remain bound by invisible threads. Along the way, we listened to the voices of those who first wondered. Planck, Einstein, Bohr, Schrödinger, Heisenberg, Bell, each leaving a lantern to light the trail. And yet, for all we have gathered, the quantum world is not closed. It is a meadow that always stretches further, with paths branching into the unknown. Some paths lead to technology, computers, clocks, microscopes, and medicines. Others lead to philosophy, questions about what it means to observe, to know, to be. Still others lead to the stars, to the first ripples of the cosmos, and perhaps to the fate of space-time itself. If tonight's journey leaves you with questions, let that be a comfort, not a burden. For in the quantum story, questions are not loose ends. They are threads that keep the fabric alive. To live in a universe that is certain would be to live in a closed book. But we live in a universe still writing itself, each page turned by curiosity, each line written in the ink of probability. So now, as your eyelids grow heavy, let us soften our steps. Imagine the universe as a quiet ocean. Each wave is a possibility, each crest a fleeting moment of certainty. You are carried gently, not by force, but by rhythm. Part of the sea, part of the stars, part of the unseen hum that holds all things together. Rest now. Let the quantum world become a lullaby, its mysteries a blanket, its paradoxes a pillow. The equations can sleep, the questions can wait. What remains is wonder, steady and kind, surrounding you like night itself. Sleep well, my friend. May your dreams be filled with ripples of light, with harmonies of possibility, with the quiet company of a universe that, even in its strangeness, is always at your side. And so our story comes to rest. May your night be gentle, your dreams untroubled, and your sleep deep. Until next time, good night.